All right, we're starting. We're live. We're live. Today we're going to learn about two to kind of three methods. We're going to start factoring polynomials. Polynomials are going to be a little bit bigger than just the quadratic trinomials that we've been factoring last chapter. So let's get rolling. First thing, yesterday we learned about synthetic division. And so today we're going to talk about using synthetic division to actually start factoring a little bit. And so the factor theorem basically states that if you are using synthetic division or synthetic substitution and you get a remainder of 0, then whatever factor you were dividing by is an actual factor of the polynomial. So when you divide by something and you don't get a remainder and it goes in evenly, it was a factor. We talked about this yesterday, right? Like 20 divided by 6. Is 6 a factor of 20? No, because 20 divided by 6 is, what, 3 2/6? Or 3 1/3? So because of the 1/3 part, it's not a factor. It doesn't go in evenly. Anywho, so let's check to see if x plus 2 is a factor of 4x squared minus 2x plus 5. So we'll use synthetic division to see if we get a remainder of 0. All right, so what makes x plus 2 0 is negative 2. Go ahead and synthetic divide, and we'll see what we get. So pull the 4 straight down, start it off. Negative 2 times 4 is negative 8. Add these two puppies together, you get negative 10. Negative 2 times negative 10 is positive 20. Add those and you get a 25. Okay, my remainder then is 25 over x plus 2, so it's not 0, so what that means is x plus 2 is not a factor, right? This is 4x minus 10 plus 25 over x plus 2. And so our conclusion then is x plus 2 is not a factor of that polynomial because remainder is not equal to 0, does not divide in evenly. Okay? All right. Next problem, it's a little different on your notes. I made it a little easier, but on here, if we have the linear term 3x minus 6, we can still use synthetic division on that. We just have to think what makes that 0, and that would be 2. So we put a 2 in the little box there. And this is a little more practical. We have a 4th degree polynomial, 5 terms. So we would start to factor this using synthetic division. See if we get a remainder of 0. Bring that down. 2 times 3 is 6. Add those, you get 0. 2 times 0 is 0. Add those, you get 6. 2 times 6 is 12. Add those, you get 15. 2 times 15 is 30. And lo and behold, we get a remainder of 0. So this is a remainder term, which is 0 over 3x minus 6. This is constant. 6 is the linear term. 0 is the quadratic term. 3 is the cubic term. Okay, so what that really meant now was 3x minus 6 is a factor. And so if it is a factor, because the remainder was 0, then we can start writing it in its factored form. We could say 3x minus 6 times whatever the leftover stuff is. In that case, that's the stuff that we got. Our quotient of our divide would be 3x cubed plus 6x plus 15. Hey Betsy, how you doing back there? Right, so now we're going to start using this to factor. Look, it's starting to get factored a little bit. It was a 4th degree polynomial, and now we got it down to a linear times a cubic. So that's what we're going to be doing as we continue on in this chapter. As we do synthetic division again, and we just keep chipping away at that like cubic stuff, and then we'd get it down to all linear or linear and quadratic, so on and so forth. So that's going to be a little bit of using synthetic division to start factoring. And the reason we start factoring these is because we want to start solving them, right? So we're going to be solving them. So like, if you just give you a little glimpse, then this would be, what would be one of the solutions if we were solving this and it was equal to 0? This would be 2 would be a solution. Same thing as like, oh, what makes the well, that factor 0? So 2 would be a solution, and you'd keep going with this stuff. You keep factoring it to get all the other solutions. Okay. Next thing I'll show you is factoring by grouping. This is kind of a neat little factoring method that works sometimes. So sometimes this works. It has to be kind of a happy little problem in order for it to work. So here's a couple, 2 little happy problems that's solved by, or factor by grouping. So we're going to take parentheses and we're going to put them around the first 2 terms there and around the last 2 terms there. And you got to be really careful to put this parenthesis right here to the left of that sign, because if I put it here, then it changes the value of the 18 to a negative. So you got to be careful not to do that. So make sure you put that parenthesis in the right spot and put it to the left of the sign. Okay. Now what we do is we factor out a common term from each of those grouping pairs. So the common term that I can factor out there, or undistribute or reverse distribute, would be x squared. Okay, so I have x squared, and then now I have left is x minus 2. And then over here I can factor out a 9 or a negative 9. I'm going to factor out a negative 9 for the reason of having matching binomial pairs here. So grouping really only works if when you group it and you factor out a common term, you get the exact same little binomial pair there. Okay, yeah.
Is there a way to like look at the problem and see like
if it works or not? Yeah, so I think you can kind of look at it and think ahead maybe and go, oh, I think that might group. Okay, because if I take, and you just think in your head whatever these steps I just did, right? And some people probably are better and more like able to visualize that than others. Some people might have to put it on paper and just determine if it does or not. So, but if it has 4 terms and it's a cubic like that, and you're not missing any like linear terms or quadratic terms, and you have all your sort of place values in place, then it might factor by grouping. So to finish this off, now we have essentially like a big binomial with a binomial term inside. It's like a binomial within a binomial. It's kind of crazy. So you factor out or undistribute out that common binomial term now. So I factor out the binomial term x minus 2, and what I have left is x squared minus 9. And you can't see this on the video, but on the whiteboard here I started writing down all the different factoring methods that we've covered so far. So we have like undistribute, unfoil, difference of squares, synthetic division, so on and so forth. And what shows up right here is a little difference of squares with the x squared minus 9. So I can continue one step further and factor that all the way down to be x plus 3, x minus 3. Question?
wouldn't you need to do x minus 2 squared since there's 2 minus 2 terms?
Yeah, that's a common thought, so thanks for saying that. She said, wouldn't you do an x minus 2 squared, like make that a squared, right? And, you know, this is kind of a hard thing, I think, to visualize, but it would be like if I was doing 2x squared, let's see, 2x squared plus maybe 6x or something like that, right? Each of these has a common term to factor out, doesn't it? Like you could undistribute or factor out a common term of 2x, couldn't you? Right? So I'm going to write this a little differently. I'm going to write this 2x times x plus 2x times 3. See? It's like the same thing, only I wrote it out in a little bit of an expanded way. Now when I factor out a 2x out of each thing, right? I just write 2x times x plus 3, don't I? When you undistribute. I did not make this 2x squared because there was 2 of them that I factored out, did I? So do you kind of see why now? It's just a little weird because we're not used to having the stuff that we factor out and undistribute be a binomial. So it's kind of written in an expanded way. Not many people can people don't really look at that and go, oh yeah, that's got an x minus 2 in it. I'll just factor that out. The way we look at this and say, oh, that's got a 2x in it. So it's kind of harder to see that. Great question. Okay, so that's factor by grouping. Why don't you see if you can take that and get started on the next one, and then I'll catch up to you. So why don't you get a little head start, and then I'll catch up. So factor this one up. We group there, we group there, we group there, we group there. We factor out common terms in each grouping pair, which would be 2x. So take a 2x out of there, and we're left with x plus 1, right? Wait, sorry. Right, let's back it up. Let's take an x squared out of there. There we go. Take an x squared out of there, and I'm left with a 2x plus 1. And the other one, take a 4 out, so plus 4, and you're left with 2x plus 1, and lo and behold, they match. So I have a match here of a common binomial pair that I can factor out. So I factor out that common binomial pair, and I have 2x plus 1 now, and the leftover stuff is x squared plus 4. And a lot of people mistake this x squared plus 4 as factorable, but it's not. There is no sum of squares, so that is as factored as you're going to get that, because x squared plus 4 is not factorable. Okay? So, and why do we do this? Why are we doing factoring and all this stuff? Just take it a little step further. We would set this equal to 0, right, and try to make it an equation we solve. And so if we were going to solve this one, we would have 2x plus 1. What makes that 0 is negative 1/2. And then what makes x squared plus 4 0? That's going to be plus or minus 2i. Because there's nothing you can square that's going to be negative 4 except for plus or minus 2i. So the reason why we're doing all this factoring stuff is to be able to solve higher degree polynomials. All right. You should see the miserable looks on some of their faces out there. This is torture. Yeah. Last thing I'll show you is a factoring identity. It's kind of like the difference of squares, how it always factors as like a plus b, a minus b. The sum or difference of cubes always factors using these identities here. And I'm going to give these to you so you don't have to memorize these. I'll put these up on the test or something so that you can use those identities, because you use them so rarely that I don't know that you would remember them like you do the quadratic formula. But I'm going to jump down and I'm going to add an easier problem to this so we can get started on it. So let's do like x squared plus 27. Okay. Oh, not squared. I did this last hour too. X cubed plus 27. So that is the sum of two cubes. So you can factor that using our sum of cubes identity. All right, two perfect cubes. X cubed is a perfect cube, don't you think? Yeah, it's x times x times x. And then 27 is a perfect cube. That is 3 times 3 times 3. I actually wrote the first 5 perfect cubes over here. 8 is 2 times 2 times 2. 27, 3 times 3 times 3. 64, 4 times 4 times 4. 125, 5 times 5 times 5. Okay, so this is going to factor using this identity, which is a cubed plus b cubed. That's just for any perfect cube. Is going to equal a plus b. That's the cube root of a cubed. So a plus b times a squared minus ab plus b squared. All right, so now your a is going to be the cube root of x cubed, which is x. And your b is going to be the cube root of 27, which is 3. So everywhere you see an a, you put an x, and everywhere you see a b, you put a 3 in. You just follow the identity. So this is going to be x plus 3 times x squared minus 3x plus 9. That's how you use the sum of cubes or difference of cubes identity. Okay, and again, why are we doing this? We're doing this to solve equations. So if this was an equation, let's say this was like, oh, solve for when this equals 0, then one of the solutions would be, because we use a zero product property, so what makes that 0 is negative 3. Or the other solution would be, this does not factor. The leftover stuff on a sum or difference of cube never factors, so this is always a DNFUQF. Does not factor, use quadratic formula part. So then you're going to get a couple of irrational or complex solutions there. Okay. Did you have a question? All right, so sum of cubes can become a little more complicated when you have something like z to the 6th. I don't like how this is written, so I'm going to rewrite it in the better order. Z to the 6th plus 8. So I put the variable first. Z to the 6th is a perfect cube. What's the cube root of z to the 6th? Z squared. Because z squared times z squared times z squared is 6 total z's, which is z to the 6th. 8 is a perfect cube. That is, cube root is 2. All right, so now when we do this, the sum of cubes again, we have a plus b times a squared plus, minus ab plus b squared. And I write the identity out every time just because I get a better feel for it and I start to remember it. So now z squared is going to be our a, so this is z squared plus 2. And then what's left, z squared squared, what's z squared squared? Z to the 4th minus 2z squared plus 4. So there, that one's just a little more complicated. And then the last one, don't forget, I have a tendency to do this quite a bit, is I forget to factor out a common term when I can. So you should always look right away if you're trying to factor something to see, is there a common term I can factor out? Because then it makes the rest of the factoring easier. So in this case, you can factor out a 2x squared, and then what ends up being left over is an x squared minus x cubed minus 8, which is, oh, I see now is a difference of cubes popped in there. All right. So now I can go and use the difference of cubes to factor that part right there. So I'd have my 2x squared, and then I'd have my x minus 2 times x squared plus 2x plus 4 after I use my sum or difference of cubes identity. Right, difference of cubes identity, that's a minus b times a squared plus a b plus b squared. Know what I'm saying? You're picking up what I'm putting down here? Am I just you're just flying through this and you're just copying down what I put down? That's good. You can go rewatch the video if you want. Or you can come up and ask me questions. Yeah. This is it right here. Yep. This is, you can't do anything more with this. Okay, you can't factor it anymore. Once you do the sum or difference of cubes, this part right here is never, like, you can't factor it anymore. So I don't think so, nope. You know, if like, maybe if this part was like a difference of squares or something within the sum of cubes or difference of cubes, maybe. All right, I'm going to sign off on the video. So, over 20 seconds. All right, let's play the game. All right, 68's a magic rule.